Okay, so last time we proved a lemma that I said was going to be useful in proving the Arzela Ascoli Theorem. So now let's actually prove this theorem. So what does the theorem say? Well, it says let Fn be a uniformly bounded and uniformly equicontinuous, and I'll define that later, sequence of functions on a closed interval AB. Then Fn has a subsequence, and let's just call it Gn, that converges uniformly on AB. So let's walk through what this means. So Fn is uniformly bounded. So just to recall from last time, that means Fn of x is less than m for all n in n and for all x in AB. So recall that means it doesn't matter which n I take, or it doesn't matter which function in the sequence that I take. It does not matter which input I take from AB. Fn of x is always going to be less than the same big M. Or in other words, big M is independent of both little n and x. So that's bounded uniformly. It's a very nice condition. How about uniformly equicontinuous? Well, that definition is up here. If Fn is equicontinuous, that means, and as you'll see, it pretty much is the same thing as a single function being uniformly continuous. It's just that it applies to each function in the sequence. So to spell it out, for all epsilon bigger than 0, there's a delta bigger than 0, such that for any 2 points in my domain xy, if those 2 points are within delta of each other, then their outputs from Fn are within epsilon of each other, but for all n and n. And that's the key, right? Because if you look at it, this whole definition up until less than epsilon, it's the same definition as what it means for a single function to be uniformly continuous on AB. It's just that instead of a single function fx minus fy, it's fnx minus fny. But the statement holds for all n. In other words, it does not matter which function in the sequence I take, the same delta will still apply. Or to emphasize, this delta is not only independent of x and y, it's also independent of n. And the way to intuit this is that this is saying that take any 2 points that are within delta of each other in the domain, right? Then their outputs cannot be arbitrarily far. They have to be within epsilon of each other. It's sort of controlling how far apart the function's values can take on that domain. That is actually what it means for a function to be uniformly continuous. A sequence of functions being equicontinuous just extends that to all the functions. Now, it doesn't, if my 2 points are within delta of each other, then each function in the sequence, right, for all n and n, their outputs have to be within epsilon. It's controlled the same way for each function in the sequence by this exact same delta. Okay? So the same delta controls each function in the sequence the same way. And that's sort of the way I like to think about this. I'm controlling how far the functions can output if their inputs are close enough. Cannot shoot too far. Same way for each function in the sequence. Okay, so long story short, I'm imposing a lot of behavior control on my sequence of functions Fn. They're bounded uniformly and continuous, and as a consequence of this pretty strong control, I get a pretty nice result out. That is, I'm guaranteed the existence of a subsequence that will converge uniformly on AB. Okay. So let's go prove this. First, we're going to set it up. Let's say here's my domain AB. And so let's start. Let Q1, Q2, Q3, so on, be all the rationals in AB. Keep in mind, the rationals are countable, so therefore the rationals in AB are certainly countable. I'm going to list all of them out, Q1, Q2, Q3, Q4. These guys are going to be every single rational number in AB. And the rationals are dense, remember, so they're going to really dot up AB and fill it right up. It's all the rationals in AB. Okay. Now, there's a little more that we know. Hold on, just going to check things. Okay, yeah. So by lemma, now let's recall the lemma from last video. It says, given a sequence of functions that is uniformly bounded and a fixed sequence of rational points, I can find a subsequence that will converge at each of those rational points. That's what I have here. It's a set of rational points in a closed interval AB. So by lemma, Fn has a subsequence, let's call it Gn, such that Gn will converge uniformly, it will converge at each of these rational points, at each Q1, Q2, Q3. This is exactly taken from the lemma, which you can recall from the previous video. This was proved by using a nice diagonalization argument. We had that nested chain of subsequences where each one converged where the previous ones did. Then we took the diagonal one, which will converge at each rational point. That's what I'm invoking here. That's what this Gn is. It converges at each rational point here in AB. Claim, a perhaps surprising claim. This Gn is exactly the subsequence that we desire. Is what we desire. That is, it converges uniformly on all of AB. And this is a bit of a surprising jump for two reasons. Number one, by the lemma, we only had that Gn converged on the rationals in AB. Now I'm claiming it converges on all of AB, including the non-rationals, the irrationals. The second surprising thing is that lemma only gave me that Gn converged pointwise on these rational numbers. It just converged there. This claim says it will converge uniformly, and not just there, on all of AB. So it's a jump for two reasons, which makes this a pretty cool theorem to me. And the way they prove it is quite neat. The idea is we're going to be using some of these rational points as goalposts from which we can catch any arbitrary value. And you'll see what I mean. So let's go prove this. So to be clear, hold on. The way I'm going to prove that Gn converges uniformly on AB is I'm going to prove that Gn is uniformly Cauchy on AB, which is an equivalent condition. So let's recall what that is. So our goal is to show that Gn is uniformly Cauchy. That is, for all epsilon bigger than 0, there's a big N and N, such that if little n, little m are bigger than big N, then Gn, oh, this is the wrong red marker, then Gn of x minus Gm of x is less than epsilon for all x in AB. Okay. So just to reemphasize, this capital N is independent of x. I can take any x from AB, and this has got to work. So keep in mind the final goal is Gn of x minus Gm of x less than epsilon. Now there is a big N for it. Holds for all x. I'm just going to re-emphasize this should be independent of x, and that's what makes this uniformly Cauchy and not just like regular Cauchy. So let's do it. So our goal is to show that something is true for all epsilon bigger than 0. So of course we're going to begin by just saying let epsilon bigger than 0. Now what? Well, okay. For this epsilon bigger than 0, recall I know that Fn is equicontinuous. So for that epsilon, there exists a delta bigger than 0, such that all that junk is true, and I'm going to make it less than epsilon over 3, which I can do because I already know Fn is equicontinuous. So for this epsilon, I can say there is a delta such that all this is true. This is epsilon over 3. So on that note, by equicontinuity, there exists delta bigger than 0 such that this stuff is true. And for this particular delta, here's what I'm going to do. Let's see if I can get this light out of the way. There you go, a little better. Consider the collection of all the delta balls centered at each rational point. So what is this? Well, at each qi, I'm going to have the ball of radius delta. Here's q1, maybe there's a ball of radius delta. That's q2, that's q3, q4, q5. Every single rational point gets its own delta bubble, same size. Okay, I think it's pretty obvious that this collection of delta bubbles is going to be an open cover of AB. After all, the rationals are dense in AB. So if I just draw delta bubbles around each of them, it should be pretty intuitive, it's going to cover all of it. And there is a way to prove it rigorously. You just invoke the density of Q and R and it'll pop right out. But this is an open cover. Open cover of AB. But AB is compact. Therefore, there is a finite subcover. Exists finite subcover. So only finitely many of these. And maybe we'll say that this finite subcover has, well, we'll say big M many of these delta balls. Let's go draw that. Okay, here's AB, a little smaller actually. So maybe the first one we take is, maybe call this one Q tilde 1. I'm putting the tilde because the first ball in our finite subcover, it doesn't have to be around Q1, right? It could be Q1000, Q1,000,000, Q3, whatever. But since I want to be able to index them, I'll just call it Q tilde 1. So maybe this is the first one. Maybe this one is, Q2. This is Q3, Q4, and the last one I called Q capital M, so we'll do that. So essentially, what I have is I can cover AB with finitely many of these balls of radius delta centered at rational points. So that finite subcover will look like this. I said capital M, I think. So V delta Q tilde I. So this is our finite subcover. It indexes from 1 till capital M, V delta Q tilde I. This is a finite subcover, so it will contain AB. But think about what that means if I take an arbitrary x from AB. Keep in mind, to prove that Gn is uniformly Cauchy, I gotta prove this for all x in AB, okay? Any x in AB. So to that end, let x arbitrary in AB. Let x in AB arbitrary. Well, since AB is covered by this finite subcover, x has got to be in one of these delta balls. So then x is going to be in V delta Q tilde I for some I, indexed from 1 to capital M. Okay, but since x has got to be in one of those delta bubbles, that means the distance from x to the center of that bubble, Qi, has got to be less than delta. And essentially what I'm saying is just draw the picture, right? Here's the Qi. There it is. And I'm saying x has got to be in, x is in one of them. Maybe x is over here, right? Well, this ball is radius delta. So if x is in that ball, then certainly the distance from x to Qi has got to be less than delta. So in other words, if x is in V delta Qi, that immediately implies the distance from x to Q tilde I is less than delta. Okay? So let's go write that. So x minus q tilde I is less than delta. But then, now we've met the criterion to use equicontinuity. Because look, x minus y less than delta, I have x minus qi less than delta. So I'll be able to say that gn of x minus gn of qi is less than epsilon over 3. I'm just going to invoke equicontinuity. So by equicontinuity, we have that gn of x minus gn of qi is less than epsilon over 3. But that's not all we can say. Remember, in equicontinuity, this whole thing holds for all n and n. It holds regardless of which function in the sequence I'm taking. So not only can I say this for n, I can say it for m too. And gm of x, and this is like a small m, minus g small m of q tilde I is less than epsilon over 3. Okay? And why do I want that? Well, it's sort of staring at you on the right. The goal was to get gn of x and gm of x less than epsilon. And look, equicontinuity already gave me, in a way, two pieces of the puzzle. I get gn and gm. Okay, so, to zoom out a little bit of this whole thing, essentially, equicontinuity gave me these two inequalities down there. So then where's the missing gap? These are two epsilon over 3s. Where's the last one? Let's go quickly do the last one. Okay, so for the last one that we need, recall by lemma that Gn converges at each Qi, at each rational point in the whole AB. So certainly it will converge at each, Q tilde 1 until Q tilde m. Certainly that will be true. So let's do it. Let's write out what that means in the epsilon form. At each Qi, that is, for the epsilon prescribed at the start, there exists a corresponding n sub I. Now, keep in mind that the convergence of Gn on the rational points, that was a pointwise convergence. If we look back at the lemma, it only was pointwise. So the n will still depend on the rational point. That's why I'm indexing ni here. In this case, the capital N does depend on the point in question. There exists ni such that if little n is bigger or equal to ni, then, it's going to be, and last quick thing, if a sequence converges at a point, then it's also Cauchy at that point. So I'm going to use Cauchiness here. Then, so if n comma little m is bigger than ni, then gn of qi minus gm of qi is less than epsilon over 3. So this is just saying that gn is Cauchy at qi, equivalent to saying gn converges at qi, which is what the lemma told us. And hopefully you can see that is pretty much the last inequality that we need. I'm going to do this whole chain together. I got gnx minus gnqi. I'm going to add the gnqi, lose the gmqi, gain it back, and then, okay, then, hold on. I'm going to, gmx minus gmqi in absolute value is the same thing as gmqi minus gmx. So, since it's all in absolute value. So, I better do do that. Okay. Now everything's going to cancel out, right? And I know it says tilde here, there's no tilde, but this is each qi, so certainly it will happen at qi tilde. Okay. Poof. We're almost done. The last subtlety, right, is that recall, to prove that Gn is uniformly Cauchy, we gotta have an n that's independent of x. That is an n that is independent of which point in my domain. If you notice, since the convergence at the rationals was only point-wise, it does depend on the rational point I was working at. I got good news. We have a finite subcover. There is only finitely many of these rational points that this qi could be. So I can take a maximum. And that's really pretty much the completion of the proof. Okay? So let's just do it like this. Gn converges at each qi, so yeah, blah, blah, blah. So certainly it will occur at the qi tilde that is the same one as from down here, right? So I could finally erase up here. Then take n to be the maximum of n1, n2, all the way until nm. Okay, so just to spell out what these big n's mean, recall I had q tilde 1, q tilde 2, all the way until q tilde m on my number line. And their delta bubbles were a finite subcover for AB. Okay. Gn converging pointwise at the rationals gives me n1 for q1, n2 for q2, and m for qm. But because x from AB has to be taken arbitrarily, I don't know. X could be in any one of them. So to make sure the proof works, I'm just going to pick an n to be the maximum of all of them, which will ensure all of these inequalities, like this one here, is going to work. Okay? So let's write that out. Take n to be the maximum of these. Then, if small n and small m are greater than this m, max of all of them, then we're going to just put the bow tie on it. Gnx minus gmx is what we want to show is less than epsilon. So gnx minus gmx is going to be less than, let's do the triple train. Got gnx minus gnqi, gnx minus gnq tilde I, plus gnq tilde I minus gmq tilde I. Okay, recall that this came from the lemma. Gn converges at each rational point. Let's just say this is from lemma. And then lastly, plus gmq tilde I minus gm of x. That's just this last term down here, which you also got from equicontinuity. So to be clear, these guys came from equicontinuity directly. But each of these we said was less than epsilon over 3, which is less than epsilon over 3 plus epsilon over 3 plus epsilon over 3, which is epsilon. And we are done. So this is a, it's a fun proof. And again, I just want to re-emphasize that these rational points, they are postmarkers. Because there's finitely many of them that cover AB, any x from AB has got to fall into one of them. But because there's only finitely many, I'll be able to take a maximum. And therefore, if my little n is bigger than that maximum, then this crucial inequality here, the one from the lemma, I can get it to hold regardless of where the x is, regardless of which one of these delta balls the x came from. And the outer two are almost fed to you directly by equicontinuity, because if x falls into any one of these delta bubbles, it automatically satisfies this condition. The distance from x to that rational point center is less than delta. Immediately we get this. That inequality is exactly what these two pieces are. So at the very least, in this video, hopefully you'll understand why we needed equicontinuity. And we needed Fn to be bounded uniformly in order to get the lemma to work in the first place. That was explained in the previous video. And you sort of get a taste as to why we needed a finite subcutter. Because only because there's finitely many bubbles, I'll be able to take a maximum. Because I can't take a max of infinitely many balls. Next video, we'll explain a little more of the subtleties behind it and how one might generalize this theorem to a compact metric space.